It is now my pleasure to introduce today's presenter, Parag Savla. Parag is an instructor with Global Knowledge. So while Parag was a student at the University of Maryland, College Park, he had a student job on campus as a network technician. He learned enough to start as a network administrator as his first job out of college. For the next several years, he took on progressively advancing roles supporting numerous commercial, government, and DoD networks. They involve networks of various sizes and a wide range of technologies. In addition to gaining valuable experience, he earned Novell, Microsoft, and Cisco certifications. In 2000, he started teaching Cisco courses for Global Knowledge and taught CCNA, CCNP, Voice over IP, and BGP classes. After a brief hiatus from technology, he resumed teaching general networking and security classes for Global Knowledge. Parag receives high marks from customers for his teaching style and product knowledge. So without further ado, I'm going to hand it over to Parag to kick us off.
Thank you, Kevin. I forgot to check, is the audio okay?
Yes, I can hear you loud and clear.
Great, thanks. Okay, welcome everybody, and welcome to today's webinar. Let's talk about what it is we're going to go over today. So first thing is, why is this foundational information on TCP/IP so important, right? Then we'll talk about the basics of the TCP/IP protocol suite, talk about some of the key protocols, IP, TCP, UDP. I'll mention some of the other core protocols as well, briefly. And we'll talk about the basics of routing, and then how subnetting pertains to TCP/IP addressing, TCP/IP addressing and subnetting, and then brief mention of IPv6, and then we'll open it up to Q&A. So first of all, why is this information so critical, right? Why do we need to know it? And the answer is TCP/IP is the main protocol used universally today. Not only at work, we use it at home, right? And of course, that's what the internet uses. So, and for all the applications, services, everything, we use pretty much TCP/IP. Back in the old days, there were other protocols that were used as well, but not these days. You know, almost the vast majority of communications occurs through TCP/IP. And without understanding this protocol suite really well, it's impossible to really design, operate, manage, or even troubleshoot our networks. So if you have a, even moderately technical role, not even a heavily technical role, but if you're in management, overlooking a team of engineers or technicians who are managing this stuff, even then you need to know it. And certainly if you are actually performing any of these functions, you have to know TCP/IP really well in order to do your job, really, right? So that's why it's so critical. Then next question is, what is TCP/IP? And TCP/IP is nothing but a suite or a collection of protocols, and a protocol being just a standardized set of rules, right? Whether it's the set of rules we use when we're talking in English here, or whether the set of rules we use when going through airport security or in a factory's assembly line, right, where you have to follow certain rules. Same thing here. Here we cannot communicate properly unless we use the same set of rules. There are actually hundreds of protocols in the TCP/IP suite, but only some are considered core, right? And so some of the key ones are, the ones being listed here. I won't read them out loud, but we'll talk about some of them, and I'll mention some of the other ones. We'll talk about some of the key ones, and then I'll mention some of the other ones as well. Right. So this slide here gives us a nice overview of the TCP/IP suite. Again, not including all the various protocols, but some of the key ones. IP is at the heart of TCP/IP. In fact, it's partly named. TCP/IP is named partly after IP. We'll talk about that. TCP/IP runs on top of Ethernet or Wi-Fi or whatever other technology we're using for physical connections. But basically IP is at the heart, and then it uses TCP and UDP, and these are the various applications. Right? So that's the idea. There are also a bunch of other protocols that are critical, like ARP and routing protocols like EIGRP and OSPF. There's also ICMP and so on. But that's the gist of how these are interrelated or interconnected, right, to each other. So IP itself, Internet Protocol, is what the acronym stands for. But if I ask you what's IP, basically you'd have to think that it's the main protocol that carries most of our data. You know, whether we go to Amazon, whether we are firing up Netflix, or you know, we are managing a network, whether we are sending email, all the data for all of those applications is ultimately being carried in IP packets. Even today, IP version 4 is the main protocol that's used, even though it's thoroughly outdated in some respects, and IP version 6 is in fact being used, but IP version 4 is still more popular. IP version 6 is newer and has been around for quite a while, but IP version 4 is still the dominant protocol on the internet today too. It is routable, which means it has a network and a host portion, and we'll talk about that in a moment as to what that implies. It's connectionless, meaning with IP, there's no need to establish a connection with the other end. IP says, whenever I'm ready to transmit data, I just will. Boom, here it goes. Right? It's unreliable, as in they call it best effort, but that's misleading too. But what it means is unreliable means there's no acknowledgments. When IP sends data, it says, I hope the other end got it. I don't know. I am not sure if they got it or not. But, you know, I sent it, is what IP says. Bear in mind there are other protocols that handle that function. So, you know, ultimately our applications and networks are not quite as unreliable as it might sound. And the address is a 32-bit long address, right? And the address is 32 bits long. So, yeah, and it's still the predominant protocol used. Yeah. Now, this is what the IP header looks like. Okay, now this might seem scary at first if you're not used to it. But if you're a technical professional who's hands-on doing a lot of the work, then this information is either something we should be familiar with, or it would be actually invaluable. And we all should be somewhat familiar with it in general if you are at all technical and using this information, right? Or you know, if you're responsible for any aspect of TCP/IP functionality. So this is what the header looks like. The top row is indicating how large each of the fields are. And this is giving us the name of the fields. And this is giving us example values, what could be in a typical packet. So you have various fields. Now, I don't have time to go over each of these fields in general, but bear in mind that some of these, right, for example, DS and ECN is basically differentiated services. It has to do with quality of service. This is telling us how long the header is, how long the total packet is, and then there's something to do with fragmentation when we have to chop up a packet into multiple pieces. That helps with that. And of course, there's a checksum for error detection, and the protocol field indicates which upper layer protocol to hand the data off to. So in IP, it's going to be TCP, UDP, ICMP. Those are the most common upper layer protocols that IP will hand the data off to, and they will hand the data off to one or the other respective application, etc. Right? So that's part of what that is. And of course, the big one is source and destination IP, which device is trying to communicate with which. So that's part of the IP header. But again, this needs to be understood in a little bit more detail, at least a little bit more detail, maybe a lot more, in order for, you know, typically technical professionals to do their job really well. TCP characteristics. What is TCP? Another very, very core protocol, right? One of very significant protocol among the core ones. TCP is connection oriented. Now, what connection oriented means is, right, it establishes a logical connection before data can be exchanged. So it's like, you know, me calling up and saying, hey, do you have a few minutes? Versus me just sending something off to you and say, hope they got it, kind of. Right? So it's a connection is established before data can be exchanged. It is full duplex, which means the two endpoints in a TCP connection, and TCP is not a group chat. It's only between two endpoints. The two endpoints can both transmit and receive data simultaneously. That's what full duplex means. It is reliable. Now, reliable is not necessarily just what we think of reliable in terms of plain English. Here, the term reliable means it will actually use acknowledgements, right? It will use sequence and acknowledgement numbers, but more importantly, acknowledgements are required. So if I send you data unreliably, that means I just send it and hope you get it. If I send you data reliably, that means I will require you to send me acknowledgments that you got the data and it was okay when you got it. Because if you don't acknowledge the data and I'm supposed to send it to you reliably, I will assume you did not get it. I will send it to you again. Right? That's one of the big things about TCP/IP, that it's reliable. And the sender side and receiver side flow control. What flow control means is if I start speaking very quickly, you might say, whoa, slow down a little bit, Parag. Or if I start talking very, very slowly, you're going to say, hey, speed up a little bit, right? So but each endpoint, each side can specify its own preference and tell the other end that I want you to speed up or I want you to slow down. And the beauty is it's dynamic too. It does not have to be fixed. It can change as circumstances change. It's adjusted accordingly, which is very powerful in some senses. And one-to-one delivery means, again, 2 endpoints only is what it means. Not like it cannot be used for group chat, like our group messaging. And it uses port numbers to identify the application. So I'm just going to scroll back real quick here. The port numbers are these numbers here. They identify to TCP and UDP appropriately what applications actually mean. What application does this data belong to? So then TCP will forward the data to the appropriate application, right? So that's what they mean by port numbers to identify the application. This is what the TCP header looks like, right? Just like in the IP header, we had source destination IP addresses at the end. Here we have source destination port numbers in the beginning, sequence and acknowledgement numbers, even telling us how long the header is. And then, window size is for flow control. Checksum is for error detection, and we have session flags and urgent pointer for other purposes as well. Okay? So that's the idea. Very significant, though. It's very important to understand these details as well. So that's TCP for us. And UDP, right? So by the way, if I ask you, when I teach, I insist to my students that if I ask them what is TCP, they should not be telling me that it's Transmission Control Protocol, right? I don't want to know what the acronym stands for. I tell them I want to hear what it is. And so typically the way I like to describe it, I wouldn't call it a formal definition, but the way I like to describe it is TCP is a connection-oriented, reliable transport layer protocol, right? It's a layer 4 protocol in the OSI model. So that's how I like to describe that. And then UDP stands for User Datagram Protocol, but that's what the acronym stands for. What it really is a connectionless protocol. Again, no connection established. That means whenever UDP wants to transmit, it just goes and fires it off. Right? I like to use the technical, use the non-technical term, right? Fire at will. Right? Whenever it wants to, it just sends it. Right? There's no checking with the other end, and it's unreliable. Sometimes called best effort, which means, again, no acknowledgments. If you ask UDP, well, did the other side get it? UDP says, I don't know, I don't care. You asked me to send it, I did. After that, it's not my problem. That's what UDP says, which means UDP is saying, really, I hope the application's checking because I'm not. Right? So that's the idea there. And then port numbers are, again, used just like TCP. Port numbers are used to identify the application itself. And of course, when you're connectionless, unreliable, it's going to be a heck of a lot less overhead. So it's much, much simpler. And as a result, at least a little bit faster. Right? So that's the idea there. Yeah. And so the point is that here, UDP's header, you can expect it to be much, much simpler than TCP's header, right? Because it's got much less functionality, and simpler, much less overhead. So that the UDP header also reflects that, right? So you have your source and destination port, length, and checksum, and that's about it. Because there's not much to do. The UDP is much simpler. There's not a whole lot to it. So this kind of puts the whole thing in perspective. Here you have your Ethernet or Wi-Fi header, if you would, an IP header, UDP header, and then the actual data. Right? So that's how it fits in the bigger picture of things. Now, what are some of the other core protocols? These are some, but not all, right? Some of the key protocols. DNS stands for Domain Name System or Domain Name Service, as it's sometimes called. Its purpose in life is to resolve names to IP addresses. Why? Because we don't remember the IP addresses of the websites or the services that we are trying to access. What we remember is the name, like CNN, Global Knowledge, ESPN, Yahoo, Amazon, right? .com, right? www. All of those things. Well, DNS resolves that name to an IP address. Because ultimately the IP packet doesn't use names, it uses IP addresses. So that's what it's got to have. And as a result, DNS is what resolves those names to IP addresses. ICMP, Internet Control Message Protocol, is used for error and diagnostic messages. And it's what helps convey error messages between devices, as well as to help for the benefit of the human, to whenever there's a problem. But it's also used for diagnostic purposes. ICMP, some of the ICMP messages are used by humans to diagnose problems, but they don't use the protocol messages directly. They use some programs like ping, for example. Right? When we use the ping command, we are actually sending ICMP messages back and forth. HTTP, of course, is the main protocol we use for browsing, and corresponding to HTTPS, which is almost the same thing except it's secure. Right? At least somewhat more secure. Let me put it that way. SMTP, Simple Mail Transfer Protocol, is what we use to send outbound mail. We actually use different protocols to retrieve email, but SMTP is what's used to send email. FTP is used to transfer files. That's what it stands for, File Transfer Protocol. And Telnet is what we use to log into a remote device, but Telnet is a command line utility, which means only commands work. Mouse doesn't work in Telnet. It's not GUI, right? There's no pretty color pictures or icons that we can, or menu options we can click on. It's all typing commands. That's Telnet for you. And of course, Telnet is very insecure, so SSH is a more secure alternative to Telnet. And not the more secure, I should say the secure alternative to Telnet, because Telnet's not secure at all. And then DHCP, Dynamic Host Configuration Protocol, is what we use to obtain IP addresses automatically. For devices to get their IP addresses automatically, DHCP server will help facilitate that, and the DHCP protocol will help facilitate that function. SNMP, Simple Network Management Protocol, is referring to network management. That's what we use to manage our networks and various devices, various components, various processes within the devices. So, for example, managing router ports or the router itself, but and the router ports or switches and switch ports, as well as various components or processes within routers, switches, printers, servers, storage devices, firewalls, etc. Right? ARP, Address Resolution Protocol, is what's used to resolve IP addresses to MAC addresses. And ARP also is one of the core protocols, of course, because ultimately our IP packets are going to ride within Ethernet frames or Wi-Fi frames. So we're going to have to make an association between the destination IP address and the destination MAC address. So ARP's used for that purpose. RTP is one of the key voice over IP protocols, real-time transfer protocol, and the SIP associated with that as well. But those are some of the key protocols used for voice over IP. That's something we need to keep in mind as well. Next big concept we want to talk about is routing. And with routing, what we have to bear in mind is that it's the process of transferring data from one network to another. Right? The internet basically is nothing but a huge collection of lots of different networks. Now, and that's just the common public network that we all access. But even in a large organization, a large company like Amazon or the school district of a particular county would count as well, right? Which has dozens or hundreds of schools in a large county, maybe not hundreds, but at least dozens of schools in a large county. So the idea there is that you would have lots of these schools. All of the schools are interconnected, or a lot of the different offices of, say, Amazon are interconnected via networks, and there would be different paths to get from one location to another, or from one site or one network to another. And routing is a process that manages that, how to send data from one network to another. There's typically going to be lots of different paths to get from one network to another. So, routers have to know about various paths. They have to know about various destination networks, and then the various paths. And then within those, each router has to be able to identify the best path to be used most of the time. So that's the gist of the routing function, right? Now, before a router can actually make a routing decision and route packets, it has to construct a routing table. And the routing table is based on, again, the information it obtains from other routers, and or itself that it has identified what is the best path to a given network. Now, so the routing decision process itself involves the router checking for every packet the router gets, and the router is sometimes getting millions of packets per second. So for every single packet that the router gets, it checks to see what is the destination IP address. First of all, in the packet. So the packet's destination IP address is used by the router to make a decision, which is logical if you think about it, right? If you say, hey, Parag, if I'm sitting in New York City and you say I'm trying to get to Los Angeles from New York City, right? So my context is U.S. based. I know many of you are joining the webinar from lots of different countries, but I'm based in the U.S. right now. So if I'm sitting in New York City right now and I'm trying to get to Los Angeles, I should go more or less in the west direction, right? I should not be going eastwards. That would be getting me to Europe, not to Los Angeles. So the idea is the router's got to have different routes in its routing table. So the routing table is going to have only the single route for each destination. Usually, it's only going to have one best path. Sometimes it can have, of course, multiple paths if they are equal. Then you can have even multiple paths, but then it'll load balance between them. But the idea is that usually you'll have one best path for each destination. But whenever a packet is received by a router, it will check in its routing table. And it'll check to see if it knows how to route that packet towards the destination. Now, the routing process is going to typically involve three options. The three options that the router is going to have are the following. One, it has either one route to that destination, in which case its job is easy. It uses that route, forwards the packet, through that route, and it's done, right? The second option is if it has no routes to that destination. In other words, the router does not know how to get to that destination. Now, in this case, the router is not going to go ask its neighbors or other routers saying, can you get me to that destination? No. The router says either I know or I don't. If I don't, guess what? That packet gets dropped. It will discard the packet like a hot potato. I don't know how to get there, and sends a message back to the source saying, sorry, I didn't know how to get to that destination. I had to drop the packet. And then moves on to the next one, right? And it's doing this all very fast. The third possibility is that the router has multiple routes to that destination. If it has multiple routes to the destination, it'll try and find the most specific route. Right? That's called the longest bit match. I don't want to get into it in more detail right now, but just know that it'll find the most specific route to that destination, and then based on the lowest metric. Right? Metric, basically, and I'll talk about that. Metric is the term used to describe the unit or measure of how far or how near or how easy to reach or how hard to reach a destination network is. Right? You and I measure distances, depending on lengths, depending on what we are measuring. Right? If it's measuring the length of a box, we use inches or feet. But if it's measuring the distance between two cities, we use miles. And if it's the distance between two planets, we use, maybe light years, right? But the point is, metric is the unit that defines or describes how easy to reach or hard to reach a destination network is. So there are various different metrics, right? And hop count is the most simple metric, right? It just says how many routers do I have to go through to get to that destination. That's not only very simple, it's also very limiting. It's not very sophisticated. It's not going to help us make intelligent decisions. Because one hop could, if I say, how many hops does it take for me to get from New York to Los Angeles? I'd say it depends on the path. Is it airlines? They have the non-stop option, right? Where there's no stops, you go directly between two cities, or there might be one stopover in between. Sometimes there's two stopovers in between, right? Depending on how far you're trying to get to and what are the flight options. But hop count, again, is not very sophisticated because it doesn't measure the distance or the bandwidth or the speed or any of that other stuff. But in a very small, simple network, it works okay. In more sophisticated, more complex networks, hop count does not work well. Right? Bandwidth, however, it will typically allow us to make much more sophisticated decisions. We'll measure the bandwidth between the various of the various links between the various destinations, and accordingly, we'll pick the path with the best bandwidth. And you can even have an arbitrary path cost designation. In other words, you can assign a cost to each link and then calculate the lowest cost for the whole path. Right? So that's another metric. Reliability and delay are other metrics that could be used, but they're not typically going to be as helpful. And load, you might even say, well, measure the load. Which link is more busy right now? That should be less used. Well, that sounds like a good idea in theory, but in reality, using the load as a metric is a bad idea because then your route keeps fluctuating. And you want your routes to be more stable and not fluctuating all the time based on things like load. So again, in theory, it may sound like a good idea, but in practice, it doesn't work out too well. But regardless, some of the other metric is used by the router to identify the lowest metric path, right? Cost, or not cost, but lowest metric path, and that's the one that's usually preferred. But one of the other things to keep in mind is in the routing decision process, the routing table is what's used, and the routing table usually only has one best path to each destination. Even when the router knows about multiple paths, it'll keep the other paths in its back pocket, but only one will make it to the routing table, the best one. And then should that become unavailable, then the router will remove the next best path from its back pocket and install that in the routing table. So that's what that is. And then routing protocol operation, right? At the end of the day, the routing protocol is what's used by routers to talk to each other, to learn about different paths and different destination networks. And then each router will figure out, based on what all it has learned, which is its best path to get to a destination. Now, the metric itself will depend on which routing protocol they're using. Different routing protocols use different metrics. So some routing protocol might use just hops as a metric. So it's, to get from LAN A to LAN B. If hops was your metric, then the best path is this way here on the 10 megabit per second link on the bottom, which basically says from LAN A, you go through one router and another router, and you're in LAN B. So 2 hops is the shortest path, but notice this is the lowest bandwidth path. The hop count did not take into account the bandwidth at all. Now, and meanwhile, some other routing protocol might use the bandwidth, right? In which case, the gigabit path is the best. And so anyway, these are the various options, right? So the metric itself, will be determined based on the routing protocol, but how they communicate with each other what kind of information they share with each other, how often they share this information. Will also depend a lot on the specific type of routing protocol being used. So different route, but at the end of the day, the purpose of the routing protocol is to simply help routers learn about destination networks and which path is better or worse than others. That's the purpose of routing protocol. I mean, strictly speaking, in a very small, simple network, you don't need any routing protocols. You can manually configure all that, and it will work. Except when there needs to be a change made, guess who's going to be making it manually? Again, we. So we don't typically want to manually configure routers to know which way to go for what network, because then, anytime something changes, we'd have to update it manually as well. And we are not going to be able to do it as quickly as the routing protocol is going to be able to. Right? So that's the benefit of using a routing protocol. And that's the gist of routing. So one of the other things to keep in mind, of course, is the fact that IP addresses, at the end of the day, are what will uniquely identify each device. So each device, including interfaces of a router, or a PC, or a cell phone, or a tablet, or a television, or a thermostat, and any such IP device, each of them is uniquely identified by its own IP address. It's 32 bits long. We don't write it in binary because us humans would have a lot of difficulty, right, processing 32-bit numbers easily or quickly. So we convert it to dotted decimal notation. We convert each block of 8 bits to a octet, right, or each octet to a decimal value and separate them by dots. That's why it's called dotted decimal. And as a network component and a host component, what they call locally administered, sometimes called host component, right? So that's what it is. Here it is. This is what an IP address would actually look like to the system, but for us humans, it's going to look like this, 192.168.10.100. If you want to play a joke on a colleague, if they ask you what's the IP address of the device you're working on, you can give it to them in binary. They won't appreciate it, but you might get a laugh out of it. And hopefully they will too if they're a good sport. But basically the idea there is ultimately the network and host portion alone is not enough. Right? We need to break up our large networks into smaller networks, and that we call subnets. So the reason we create subnets is because many of the default networks are also still too huge. We don't need such large networks. We need much smaller networks called subnets. And oftentimes, a network would be a single network. We need lots of smaller networks called subnets. So the reason for subnetting is to what? A, because of the fact that we need multiple smaller networks instead of one larger one, and to make networks more manageable, to help reduce the waste of addresses, we subnet. Now, subnetting is a big thing, and a lot of students often get confused with that. So, there are lots of things we need to know in order to understand subnetting. Yeah. And also, while trying to subnet, we need to be asking certain questions about what all, not what all, sorry, but we need to ask certain questions to obtain certain information to then subnet in a more logical or intelligent manner. Right? So how many broadcast domains, by broadcast domains, they mean subnets, right? How many do we need? How many host addresses or how many IP addresses do we need per subnet? Right? What is the total number of addresses we need, right? A total range of the addresses that are available to us. What is the potential for growth? Will each network grow in number of hosts, or will we need more subnets later, right, is what we should be asking also. Now, before we can understand subnetting, the process itself of calculating all these values, we need to first understand, be very clear on why we need to do subnetting, right? Or what is the purpose really? Not more than why, what is the purpose of subnetting? So that's a general thing. It's not going to vary depending on each environment. In general, we must understand what is the purpose of subnetting. And we have to understand binary numbering. We have to be able to convert binary to decimal and vice versa. We have to understand the IP address classes, ABC, etc., the octet boundaries. We have to understand the subnet mask and the rules, how they work, right? What are they helpful for? And we have to typically have a very clear understanding of how many bits will give us how many hosts or subnets. Or depending on how many subnets or hosts we need, how many subnet or host bits are we going to need? So that table typically that we have to construct or we have to look at, that'll give us that corresponding information. And we have to be able to count the bits. We have to be able to very quick count or identify how many bits are in the network portion, how many bits are in the subnet portion, how many bits are in the host portion. And one other piece of information is the prefix notation. Like the masks are often written as /16 or /24 or something along those lines. Got to understand that. Then only can we really understand subnetting. Otherwise, we can use a subnet calculator, but we won't know anything what's going on. It's like, for me to be able to drive a car, I don't need to know how the engine works. Well, in the case of subnetting, if I had to do subnetting, then I need to know all this. Right? So think of us as being the car mechanics. For us, we need to understand how the engine works. Being a regular driver is like being a user. For them, they don't need to know subnetting. The other analogy I like to use is that of a pizza, right? The entire network before the pizza is sliced is the network before subnetting. And the slice is the equivalent of a subnet. And so when we slice the pizza, we get the various subnets. That's the kind of analogy I like to use. And think of these toppings as addresses for hosts, right? That's kind of how I like to explain it, but that's just one way of doing it, right? That's ultimately the idea is to calculate the addresses we need for our various hosts or various devices. IPv6, again, it's been around for quite a while. Many countries use it far more than v4, or IP version 4, but at least in many parts of the world, IPv4 is still used more predominantly. IPv6, however, has a much bigger address, 128 bits versus just 32 bits. So we'd never run out of IPv6 addresses again. And they provide a bunch of, so it's not provide, sorry, let me rephrase that. In the basic IPv6 header, they actually took away certain fields. Remember I showed you the IPv4 header earlier? Some of the fields have been taken out from the IPv6 header, but then you might say, whoa, wait a minute, does that mean we lost some functionality? Did they actually reduce the functionality with v6? You would think they would add functionality. Well, they have added functionality, but the reason they took out some of the fields from the basic header is to keep the whole process simple and more manageable. So they don't force all devices to deal with the various fields. They made them options and extensions. So the other fields in the IPv6 that were taken out from the IPv4 header have been made part of the extension or option headers. And so the functionality still exists, but not everyone is forced to deal with it, which is kind of nice. So that actually simplifies the protocol to some extent. It also, IPv6 still maintains quality of service, which IPv4 has. It also has better security, and that's because IPsec, IP security, is an integral part of IPv6. It's automatically built into IPv6. In fact, it was developed. IPsec was developed for IPv6, and subsequently it was ported to IPv4 as an add-on, right? And so those are some of the big ideas there. But ultimately, the big thing is we won't run out of IP addresses, and it does incorporate some flexibility and some other capabilities that v4 lacks. So it's very powerful in that sense. Migrating to IPv6 though is a slight challenge. It's not as simple as flipping a switch and saying, okay, we'll use IPv6 now instead of IPv4, right? Migrating to IPv6 is a slight challenge because it is completely different in some respects from IPv4. The address size is different, the header is different, so they can't talk directly to each other. So migrating is a slight challenge, and that's one of the reasons why many organizations haven't migrated yet, right? All right, so I wanted to share a few jokes with you guys. So I'll let you read it. I won't say it out loud, and then we'll open it up to Q&A. So I'll leave this up for a few seconds for you to look at.
All right, Parag, thank you for today's webinar. That was great, some information. We do have a few questions that we'll address now, and then if there's additional questions, please include them in the Q&A. So the first one came through was, do you have any recommendations on some good books or reference materials regarding this subject?
Okay, so I haven't looked up a recently written book on TCP/IP, but the author Comer, C-O-M-E-R, Douglas, if I'm not mistaken, is that's a classic. Because I started with TCP/IP a long time ago, I own the book somewhere. I don't know, but I have it. But yeah, that's one that comes to mind. There was another one by maybe Black is the last name of the author. I want to say TCP/IP Illustrated was another set of books, I think, that was also very highly regarded and a classic. But Comer's book on TCP/IP, I think, if I'm not mistaken, is a classic as well. So try those.
All right, thank you.
Yeah.
So another question. What is the difference between level 2 routers and level 3 routers, and how does this change the routing decision process?
It's a little hard to explain that. So I don't know if you're referring to, and I'm going to take a shot because you may not have a chance to clarify the question. But with layer 2, if you're referring to OSI model layer 2, it's not routing, it's switching. And layer 3 is where routing occurs. Now, level 2, level 3, sometimes organizations may call their routers level 2, level 3 because of the layers in which they operate. The higher the number, I suppose, it's more aggregation. Think of it just as a pyramid, right? It's a pyramid. So the higher level router is connecting more, further apart networks together or whatnot. Or it's aggregating. A level 3 router would aggregate level 2 routing information or routers, and so level 2 routers will route within a certain region, and then if they need to go beyond, they would send it up to a level 3 router, and then it would route further out, is my guess, right? But I would need to have a little bit more specifics to answer that question more clearly, is what I would say. Yeah, hope that helps.
All right.
If not, please clarify.
Yeah,
sorry.
we still have some time. We have about just under 15 minutes before the top, so we can go ahead and you can insert a follow-on question if you like. So another question is, what are the reasons IPv6 hasn't been widely adopted yet?
Very good. Good question. I would say the biggest reason is because the pain to migrate to V6 is greater than the pain of living with V4. V4 works for the most part, right? We have basic functionality. If you have enough addresses and basic functionality is in place, it works. The U.S. Department of Defense, for example, is supposed to have migrated to IPv6, a long time ago, and that deadline keeps getting extended and extended. Again, because it's just simply for that reason, because it's not trivial. You can't just flip a switch and say, okay, let's use V6. It's not like a push of a button or a selecting of a menu option. There's a lot to it. There's a lot that needs to go happen before we switch over to it. And so as a result, the pain, I would say, of migrating to V6 when it's greater than the pain of continuing to use V4, then you don't migrate, right? But when the day the pain exceeds the pain of living with V4 exceeds the pain of migrating, then we would. That's typically the reason. So, for example, there are countries that have migrated to V6 or used V6 because they didn't have enough IP addresses. So they flipped the switch to IPv6 a long time ago, and they've been using the more dominantly IPv6. So I hope that helps.
All right, so we have a question on the OSI model. So what is the difference between the OSI 7-layer model and the TCP TCP IP 4-layer model?
Okay, so it's just the difference is, or first let me explain that both models are fundamentally categorizing the different functions involved in networking in a different way. That's all. So what the OSI model, calls layers 1 and 2, the TCP/IP model calls the network interface layer, the single layer combining those same functions. It's just a different way of classifying or categorizing these functions, but otherwise it's fundamentally this, same thing, except TCP/IP model is less granular. It's a simpler one. It's also not as popular, by the way, even though it exists. It's not as heavily used. For example, when I'm troubleshooting networks, I'll still refer to the OSI model layer, not the TCP/IP model layer, right? But otherwise, there's not much difference. The same set of functions, just classified or categorized, organized differently. That's all. Yeah.
All right.
Okay.
It looks like we got some questions in that chat, so let me flip over there. So what would be a good book or reference materials for prepping for the CCNA? I assume the CCNA routing and switching is what they're looking for. So selfishly, I'll take that one initially. We have great courses at Global Knowledge that cover that specific topic. But if you're asking for a book that you can purchase off the shelf, Parag, do you have any suggestions there?
I used to teach Cisco classes. I haven't taught them lately. Cybex, I know, has traditionally been a very good study guide. And typically it's going to be about 1,000 pages, or several hundred pages. But those are usually pretty good. I haven't looked at the latest ones, so I can't say with more certainty. But in the past, when I've seen them, they're real good. But again, when you have so much material, it's you're going to end up learning a lot anyway. But so most books that are that length will do okay. But in the past, I like the Cybex ones. Yeah. Sorry, I can't give you a more definitive answer.
All right, thank you. And then again, we are one of Cisco's most trusted learning partners, so we certainly have classes that help students prepare for that specific exam. So please check that out. So the next question is, can you go over the CIDR again, 1624, and what it means?
Okay, so that's, I wouldn't call it /16 or /24 CIDR, CIDR. It's pronounced CIDR.
CIDR, okay, my apologies.
But no, that's not. I'm not complaining to you. I was just clarifying for the benefit of the person who asked. So CIDR stands for classless interdomain routing. What that is that says, look, with class-full addressing, we are especially concerned about what is the class of the IP address, and we have to take into account what the class is, and accordingly, make decisions and apply a certain information accordingly. But with classless interdomain routing, CIDR, what it's saying is, look, don't worry about the class. Who cares what the class is? Here's an IP address. Here's a mask. Just do it. Just use it. And that's what CIDR is. Now, the prefix notation, that /16 or /24, is a separate idea. That's called the prefix notation sometimes. CIDR uses the prefix notation just to designate or to represent, the mask. But the prefix notation is used to represent subnet mask. So what you and I would call a mask like 255.255.255.0, it actually has 24 ones in it. And that's why we write /24 to represent the same thing in a more compact form. That's all it is. For example, /16 is really representing 255.255.0.0 because that has 16 ones in that mask. And that number is representing how many ones there are in the mask, is what it is. So even if you see a /27 or a /30, it means there are 27 or 30 ones respectively in that mask. But instead of writing it out in dotted decimal, which is much longer form, that you're just abbreviating or summarizing it with the prefix notation. That's all.
All right, great. A few more questions, and then we can wrap up. So obviously, the topics you covered today is great, but we definitely can go deeper on this topic. So can you share what a student can expect to experience if they elect to attend the full 5-day TCP/IP course?
Sure, Kevin. So here's, and I love teaching, by the way, that class also a lot. partly because I get students in my more advanced classes I teach without that basic knowledge. And when they come in more advanced classes without that knowledge, they're lost, they're confused. And when I'm trying to teach them more advanced concepts, they don't understand that because they don't have the basics clear, right? The TCP/IP class actually breaks out those headers I showed you, not only the IP, TCP, UDP headers, but it breaks out the DNS, DHCP, ARP, and numerous other headers, right? That I actually explain in class what is the purpose of each and every field. Then, after having gone through that lecture, they actually get to look at those fields and the actual headers and how they work, how those fields are affected, how they are manipulated, how the devices process the information in those fields in labs. And these labs represent real life stuff, right? Because TCP/IP is used everywhere. It's very easy to simulate real life networks in a lab setting, and while still making it very real, very practical. So they actually get to experience it. They actually then see how it works. The light bulbs go on big time. And so they walk away every single day, not only at the end of the week, but every single day they walk away with very practical information that they can apply immediately at work, at home, anywhere they want, anywhere TCP/IP to use. And so those are the big things I like. And because now they also get much more insight into how the protocol behaves, how it works, and it all makes sense. In the past, oftentimes at work, we've been told, just do this, it works, or do it this way because that's the way everyone does it. But now you get to understand at a deeper level also and see it in use, and it all clicks and fits really nicely together. Right? And there's time to do it, in a systematic manner. In some classes, sometimes things are so rushed, it's hard to get things in detail. But here there is time to do it nicely and get a good explanation. And of course, the biggest benefit also, and I shouldn't say biggest, but one of the big benefits is you get a live instructor who can hopefully explain things to you if something is confusing or something's not clear. Now they can really clarify things really nicely and explain things, clear your doubts, So those are the big benefits, I would say.
Great. All right, we just have a few more minutes, so we're going to cover just a few more pieces of information that I'll share with you. So in the meantime, Parag, if you can look in the chat within Zoom, there was a question of verification on the resources that you mentioned with the various authors, Ulysses Black and Douglas Comer and Richard Stevens. We just want to confirm that those are the ones that you would recommend.
Okay. Yeah, that's correct. Interconnecting with TCP/IP by Douglas Comer is right. TCP/IP illustrated, yeah. So TCP/IP illustrated by Richard Stevens is correct. And the one by Ulysses Black, I don't remember quite as well, but I think it was one of the highly regarded ones. But definitely the illustrated and the book by Comer are the ones that I have read personally, and those are pretty good. Yeah, that's
okay,
correct.
Perfect. All right, so if you want to just advance to the next slide. So we appreciate everyone's attendance today. If you're looking to get further into this topic area, we definitely have a great course that we just referenced, and the slides from here were built from that, but we definitely go deeper in the 5-day course, and that's the TCP/IP Networking Foundations course. If you take a look at that outline and it's something you might not be ready for, then we have a great Understanding Networking Fundamentals class that you can take a look at. And then beyond that, once you get through both of those classes, you can start looking at some more vendor-specific courses like Cisco and Juniper. Or if you're using Wireshark, there's a good troubleshooting class there that will advance your skills. So as an attendee of today's webinar, we definitely appreciate your time and your participation. We want to offer you a 25% off discount on your next Global Knowledge Delivered course. So there are promo codes listed on the screen here. You can use those when you sign up online, or if you are in contact with your Global Knowledge account manager, please provide these codes and you can go ahead and get signed up with a discount. So finally, be sure to, if you have additional questions, we have some handles here for you to take a look at. We have social media handles for you to reach us out to, but by all means, please visit globalknowledge.com for additional white papers, courses, special offers. There's a lot of good information on there. This webinar will be posted there as well. So you can use that as a future resource. So I'm going to take a quick look at the chat one more time to make sure there's no more questions. I think we covered it there and in the Q&A. It looks like we're good there. So we appreciate everyone's time. This concludes today's webinar. Parag, thank you very much for your time today, and everyone have a great rest of your day.
Thanks a lot, Kevin, and thank you all for participating in this. I hope this was helpful to you guys. I wish you guys all the best, and look forward to having you guys in one of our classes as well. But regardless, wish you the best. Keep learning, and hope you guys grow in your careers. Yeah? Thank you.